Today we are talking about exponential functions in context. There is a lot of overlap between exponential functions in context and linear functions in context that we covered a few units ago. It may be helpful to you to reference those as well. As always with functions in context, you should read the context before you do anything else. For example, in number 1 it says, you would like to have a pool party, but the water heater just got fixed and will take time to warm up. Right now the water temperature is 50 degrees Fahrenheit, and the repair person says that it will get 9% warmer every hour. So our starting place at time 0 is 50 degrees Fahrenheit, and we're going to expect this to grow. We want the temperature to get higher. So this is going to follow a growth pattern. Explain what each part of the function 50 times 1.098 to the h represents in the situation. Well, as we said, 50 is our starting temperature. We're talking about h hours. And we say 1.09. But you'll notice up here it only says 9% warmer each hour. So if we were to take that 9% and write it as a decimal, it would be 0.09. However, if we just plugged 0.09 into this function, it would be decay. The temperature would be going down. Why we write 1.09 is because this is the same thing as 1 plus 0.09. If we were to write this as a distribution problem, this would be the same thing as 50 times 1.09. So this is inclusion of the original temperature plus the change. This is the biggest idea from this particular paper. Make sure that we can understand that when we're talking about growth or decay, sometimes you have to talk about the whole and then add on the change as well. Use this information to complete the table and sketch a graph. So at time 0, the temperature is 50 degrees. When the time is 1, we can plug in 1 and 2 for our hours, and we get 50 times 1.09 to the first power, which is 54.5. At this point, you'll probably need a calculator. This is stuff I can't do without a calculator. 50 times 1.09 squared is, I believe it's about 59, but I'm just double checking really quick with my calculator. It's 59.4. At this point, let's go ahead and just graph some of those points. So we'll start with the temperatures. I'm going to start at 50. I'm going to go up by 10, but you have a lot of control over how you scale your axes. So we start at 50. I'm going to do my points in blue. First hour, it's 54.5, which is right about there. Our next point is 59.4, which is right there. And it'll eventually go up, 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 and up. We can plug in a few more points. So that's going to be 50 times 1.09 cubed is going to be 64.7. So that's going to be right about there. 50 times 1.009 to the fourth is going to be, sorry, I'm just doing the math on the calculator as well. 70.5, which is right about just above 70 there. Fifty times 1.09 to the fifth power is 76.9, which is just right about there. And our last one, 50 times 1.09 to the sixth, is going to be 83.8, which will be right about there. So you'll notice the rate of change is not getting big very quickly, but it is getting slightly bigger over time. In this context, would the function be discrete or continuous? For me, I always ask myself the question of, does it make sense to connect the dots together? In this case, I'd say yes, because we could, at times that aren't directly on the hour, go and measure the temperature. So I'd say yes, this one is continuous. And approximately when will the temperature be 82 degrees? About right about in between 5 and 6, so I'd say probably about 5.5 hours. Let's go ahead and look at number 3. Number 2 is very similar to number 1, but let's look at number 3. That one's a little different. So in this case, we have someone starting a rumor that BTS is coming to their school. On the first day, she tells 3 students. The next day, those 3 students tell 3 more students. So we have 9 students that know the secret. Third day, they tell 3 more. And we get 27 students that know the secret. Fourth day, 81, and it follows the pattern y is equal to 3 to the x. Now you'll notice when we get down to somewhere like here in the 9th day, that number is going to be very, very big. In fact, 3 to the 9th power is going to be, I'm currently doing the math on that as we speak, that's 19,683. If it gets tricky when you're graphing things like this, I would scale your scales to deal with big numbers like that as opposed to being accurate on the smaller numbers. The reason being, asymptotes. Exponential functions have asymptotes, or lines that they never cross, and that information is generally less interesting to us than the numbers when they get very, very big. So graph things so they're accurate on the bigger numbers. As always, let me know if you have questions.